Good afternoon. I tried not to let you slumber to sleep at the lunch, so I'll talk about an ending study led in CNES. This study is a 200 study with a science head, Baptiste Cecconi, and unfortunately for you, I'm not a science head, and so I'll beg for your indulgence if of my history of a science subject in this talk. So I try to give you some key information, and the purpose of the talk is to put this information on the preliminary results of this concept study dealing with a low frequency radio astronomy interferometer in space. First of all, radio astronomy is a young science, and very quickly the need of multi-point antennas rose. Along with space-based instruments also, but for the moment, array antennas have been only deployed on the ground, and only single-point measurement radio instruments are in space. We'll see that the low frequency range we stop at roughly 100 megahertz is poorly observed a little from ground with recent radio antenna networks such as LOFAR, for instance, of CNES and the rare space instruments are only one measurements, so you see the whole sky in a single measurement. The now complex and rich radio networks exist on the ground. For instance, so far as I cited, is set in Netherlands and spread among the whole Europe now, and achieves a very new observation with capabilities. The problem is the limitation of ground instruments is due to the ionosphere and cut off at 10 megahertz, and roughly an interferometer LOFAR cannot see anything pertinent below 50 megahertz. The other closest human activity that is quantity measurements in the Earth vicinity. So the idea is to get off in space for this kind of measurements, and the idea and the rise of nanosatellites may give access to new opportunities to put radio instruments in space with numerous measurement points, and as we'll know, simplified instrumentation. Already some radio instruments have flown on CubeSats, so the feasibility is done, and even pertinent science that have been acquired. And the concept of multiple measurement sets needed for new architectures and distributed instrumentation with any application in space weather, with a widespread network of measurement points, and of course radio astronomy with synthetical large antennas deployed in space like they are in ground observatories. The access to low frequencies under 30 megahertz is a new window to open to the universe, since we cannot observe it from the ground, and multiple science thematics have been identified as potential clients of this kind of instrumentation, from the toughest cosmology that needs very sharp angular resolution and very high sensitivity to probably the simplest to access, such as solar physics and solar events that are powerful events that can be observed even in the Earth's vicinity, despite the already frequency interferences. So the nanosat platform opens a new way to design the instruments on the scheme of distributed instrument and interferometry. Of course, we are not the first to have this idea, since numerous studies have been conducted and some are ongoing on this subject, with various configuration, various sizes of the space system seen as an instrument. Probably the one that inspired the most NOIRE is ALPHA, from the Netherlands team that made LOFAR, the ground observatory, which is more or less the same configuration than the one studied with NOIRE. So the study was led by a very rich team with core labs and agencies and other partners in labs and universities, and of course a strong interaction with the Netherlands team of LOFAR. The first step of the study was to establish the science need very precisely, listing all the science domains, science objectives. We use a certain number of tools to achieve this activity. The first science traceability matrix shows science topics, observation objects, and we tried to have a detailed characterization of this phenomena in terms of spectral characteristics, signal magnitude, signal resolution, time consideration, and also leading to sizing of the space system needed to achieve this measurement, this kind of measurement. In this slides, you can have an idea of the graduate difficulty from a thematic to another, and the NOIRE concept appears as a generic one that could be tuned for depending on the science objective that will be targeted. From the space point of view, for the moment only, as I said, single point measurements have been achieved by radio instruments in spacecraft such as Cassini, for instance. And the fact that it's a single point measurement only gives access to the spectra, either in flux, the colored chart, or in polarization, the grayscale one. And the 3D representation at the bottom right cannot be directly produced by this single one-point measurement, and is obtained by means of strong hypothesis on the direction from where the emission, from the kind of sources, from the form of the wave, and so on. So this kind of representation is not obviously true. What we can expect with an interferometer as NOIRE is to have a real imaging representation of the phenomena and of the radio sources, such as this one obtained on Jupiter, I think, with LOFAR from the ground at higher frequencies than the one we target with NOIRE. Another example of the progress we expect to make with that is on solar emissions. Such a chirp, either red than a cold chart on the left side shows, is supposed to be due to an emission from the sun outwards, and it can be modelized by this bubble diagram that represented the error on the trajectory of the emission. So it's something unprecise at the moment, and we expect that with interferometry we could have an idea on the repartition on the space, the spatial repartition of the phenomena, and even, why not, the shape, the actual shape of the emission. At last, the kind of data a ground observatory may give today at higher frequencies, like the radiation belts of Jupiter, for instance, could be obtained on the Earth at lower frequencies, and the right-hand simulation show what we could obtain as a measurement instead of a modelization with NOIRE. So the instrument concept is very simple. Each node of the nanosatellite swarm is equipped with a single 3-antenna device with digital conversion and pre-processing in order to make sub-bands that could be parameterized depending on the object to be observed. And after that, a distributed processing in software. Because this synthetic antenna is capable of beamforming either a single beam pointing in one direction if a very, very low signal is to be observed, or even several beamforming are obtained by way of phasing and weighting of the individual antennas, and coherent sum can be achieved in a dedicated one or several computing nodes to have a pre-processed interferometry on board the network. That's why we try to push forward a certain number of technical concepts to have to address the ideal instrument, which is spread over the space system. So these keywords are homogeneous swarm. Each node is every node are identical and capable of any of the function of the processing chain. The second keyword is low control. No need of a straight control of the swarm formation. No active formation flying. But knowledge is mandatory for the processing. So either the movement, the attitude, and the orbit of the individual nodes has to be monitored. For that purpose, we pushed forward a relative navigation concept based on the same principle of GNSS. Each node in the swarm uses the others as a GNSS constellation that gives 2x2 baseline measurements, and progressively you can have all the baseline measured for an instantaneous position of the swarm. Of course, time knowledge is mandatory, either for the processing and also for the relative navigation tool. And another level of navigation is mandatory because 2x2 distances are not enough for restituting the shape and orientation of the swarm in space, and of course to determine the direction from where comes the signal you observe. The idea also is to lower the volume of the data to be delivered to Earth by onboard processing spread on the network, and the necessity of a network at swarm scale is pushed. Yeah, okay. Based on the communication on the same link as the relative navigation. So we had some orbitography simulation that supported the ranging and the ranging simulation, and as well as simulation of beamforming. This kind of simulation has been done that shows that the beamforming capability is able to resolve small angular size. There are a few degrees in space. The first ranging concept has been three-dimensional with a theoretical capability of centimetric measurement. Yes, okay. And we have some direction of further studies, and particularly I'm in charge of establishing and conducting a technical maturation plan on these topics to go forward on this concept. Thank you for your attention. Any questions?
I I know the answer, but I think it's interesting for people. What is CNES position regarding this kind of nanosatellite concept today?
Today, the CNES position is to somehow separate the science reflection on the mission and the space system infrastructure, because the studies show that this kind of nanosatellite swarm is capable for other mission than this one. For instance, Earth observation mission. Of course, we had already this idea of space weather. So the technical maturation plan is led by this generic space architecture concern to be pushed forward for feasibility demonstration, which is not acquired yet. And the radioastronomy is a thematic that will be instructed through the next science seminar, perspective seminar next year.
You say you don't add the active control for maintaining the cluster. Did you check whether the baseline will involve too long that you can build a connection between the satellites?
I said that we want to go in this direction. Of course, the first formation of the swarm after release by the carrier need active control to avoid the nanosat to spread across the space. To have a first formation after that, we hope that we can relax the constraint on the control in order to minimize the propulsion and power to push in this.
So you still have an active control after release?
Just after the release, we need an active control to form.
But the baseline can involve, I don't know how long.
The question is long-term evolution. Yes, it has to be refined, of course.
Any other questions? In that case, we'll do it for our next talk. Bye bye.
Yeah.